part being the least in my mind. We'll discuss the way that next level logic. Most of us aren't really smart, so just put it in and make it go and do what we want to do.
Good idea. Yeah, it's just like traditional which no, so what other
well, I work for organizations like information organizations, so like trying to involve like trying to organize some way to identify like the messages and contacts, links that are related,
right more of the unsupervised world.
Yeah, but mainly unsupervised. I mean, the only deep learning practices that I think
Off the shelf
my theory is take like the biggest sort of state of the art embedding. So, usually most models kind of like in the light. Large, so take whatever state of the art, take the large, and go with it, because it's something like training your own. You don't have that much data. You would pay, but screw it out and be the benefit out of it.
Kind of in the middle. It's going to take a year for it to load.
All of Wikipedia has got
I've got the wish list. The wish list would be so what this with us. I'd like to think some of that okay. Maybe part of that is, at least from my perspective,
so the explanation is that let's say
I'm already pretty fast.
Classification on sort of one-shot new example.
I want to get to a small field for
so what you do,
No, you're not the little Ricky just did.
Or it's usually a multi-line process.
So if you turn it into a binary by saying
What you do is you have a single network.
The list is on here. Some of them, each one is here. Much more than that.
And you look at the difference between outputs of that network. And if they're in the same class, you backpropagate to reduce the distance.
Yeah.
If they're different classes,
everybody. My name is John Ramey. I organized this meetup alongside of two people that are over here. They both have some things going on. The buyers are here. Thanks for coming out. We meet, if you're new here, this is the Austin Deep meetup. You see a lot of familiar faces here. If you don't recognize, this is the Austin Deep meetup. It's not blockchain or some other buzzword type technology. We meet once a month, every second Tuesday. There's an advanced journal club that meets 1 to 2 times a month. If you look on the meetup site, you'll see journal club. We are looking for white papers. We do a lot of interesting stuff. So if you're not familiar with that, check it out. One thing we plug almost every time we're out here is we do have a Slack channel. I just spammed everybody twice this week to say this is how you get on this Slack channel, because even though there's the link to the Slack channel is probably on 5 different places on the meetup site. You can still come to me and say, how do I get on the meetup site? So it's on there, I promise, but if you don't find it, talk to me. One other thing, so we've had a long-time sponsor. They are no longer our sponsor. We are looking for a new sponsor or sponsors. Please see me after if you'd like to talk about a sponsorship. Appreciate that. I was working on a couple, and one of them I really wanted to not get out. So anyway, please talk to me, Matt. Please talk to me after about a meetup. We have a lot of really good talks coming in the next probably 6 months. Unfortunately, we've been overwhelmed with high-quality talks. But that said, when there's a lot of high-quality talks, we can choose which one we think not only is the best talk, best topic, but the one that we think matches what people want to hear. So if you have something in mind, please see me after, and I'll ask you a bunch of questions. It's a standard set of questions I ask everybody. One final thing, after this talk, we'll be 45 minutes from now, maybe an hour, depending on how many questions and such. We always meet, we go to Scene 29, there's a cocktail bar right across the street. It's literally right there. Please join us, usually 10, 15 people. We come and we have a pretty big conversation. So without further ado, I'd like to introduce Mark Landry. I've known Mark for quite some time now. I'm from the meetup scene. Very intrigued by what he offers to speak tonight. Thank you.
Really loud. Screens are maybe going to be a bit small. Of course, we'll get this all the content out. Get a repo, get that out. So, we've got the H2O logo in the top. This is actually a talk kind of repurposed, but completely repurposed. To quite a bit rough on the edges, but to be really deep learning focused. So it's a project we're doing at H2O where I work, and I did a presentation about at a really high level about what we're up to for H2O London just a couple weeks ago. So I happen to have a few slides, and in the end, only a few of them made it, but it was a good opportunity to dig deep myself, to actually pull out the paper, and I saw Danny had it printed earlier. I really like the paper that's based on. We'll take a look a little bit at the implementation, not so much as deep as just a dive maybe, but the paper is actually.
I don't have to talk so loud anymore. Unless we want to start again, but for the live stream. But so we're talking about this. It's a talk I've done for sort of business purposes. So at H2O World Conference we had in London about 2 weeks ago. I did a talk through this, so we happen to have something canned, and we needed a speaker, so here. But I have tailored this a lot towards this the deep learning crowd. I have very little deep learning in it. A brief bit about Retina Net, and that's the focus here. So let me go show you what the structure is going to look like. So try to pretend we're going to put this in a graph, but because it is really several things coming together that really is what we're going to talk about here. So first, we're going to look at our team here at H2O, the people doing the work that I'm going to show you. So this is actual applied deep learning, really. That's why it's going to be not so much a deep dive, but maybe a shallow dive or a dive of some sort. Object detection is another one of the principles that comes together. So looking at that technique. So looking at the Slack channel, I don't know that there's been an object, didn't look like there's an object detection talk in a while, so we'll kind of go over where that's gone in the last few years, how you go from CNN to where we are today, specifically diving into Retina Net. And after that, we'll kind of combine with this business task we have. So those three things kind of all come together, and I'll share a few of our results, take a look at our code a little bit. We're mainly using the implementation. It's pretty easy to use, so that's part of why we're using it as well. And time permitting, we'll talk at some of the lessons learned and some of the things that we've kind of struggled to learn. We've been doing this for about 3 months now, so we started in August. The idea came up maybe in March. So we're still early on the journey to actually getting somewhere, but we're definitely using several different object detection techniques, and we can see some of the results of some of those. So to start, our team. So put this here. It's kind of a Kaggle-led team, and I put this. I'm on the bottom, and my top finishes are all in the tabular data side. So I'm not exactly the expert that you'd hope for giving this talk, but my team members are. So I'm going to try and talk through their work as much as possible. So I know my way around Kaggle, but Brandon on top. Brandon Murray is the other data scientist who's been working for us for about 2 years. He and I, and he is excellent at Kaggle, Kaggle Grandmaster, only about 100 of those. But more importantly, he knows his way around deep learning too. So 5 different top 20 finishes in Kaggle competitions involving deep learning. And then Shaikh Galib is a deep learning specialist, actually. So he's done only 15 of these, kind of does them for fun, and so lucky enough to connect with him, and he's been really good at these as well. So we've had, and also in the audience we have Shanshan Wang, kind of our 4th team member. So Sheka and Shanshan are very new to the team. Brett and I have been working together for a couple times. So we're going to combine that kind of Kaggle look at things to solve this problem. Now, the problem I'm going to show you isn't entirely deep learning based. We're going to pretend that didn't exist and just look at where we're going with deep learning here. To some extent, there's a lot of NLP. Now, NLP is deep learning too, but we're not going to look at RNNs or LSTMs or anything of that type. We're going to look specifically at the image stuff. So, also here, because we're sort of unofficially expanding. So, if you're interested, our plans call for our team to grow. So we would certainly be interested in talking with people who knew their way around some of these technologies that we're talking about, or even interested in kind of learning. So let's get into object detection. So this will be the main part. So object detection starts with image recognition. It's kind of, the 2006 kind of version of this is where CNNs and Dropout, all that good stuff came from. Lots of awesome data sets that are out here, but if you look at the bottom, all these data sets, the object recognition portion, you typically have a picture and it's got sort of one thing. It's fairly obvious what you're trying to recognize in these, and this is where the world was 10, 12 years ago, all of a sudden the results with deep learning got much better. I'm sure we pretty much all know that at this point. So once you do that, how do you solve this one? Do you break it apart into lots of little images and send each of those in? Kind of is the answer. But the point here is that there's many different things. And this is, you see a lot of this. The self-driving cars are pretty innovative about getting this done, although a lot of the work that, in fact, the paper we'll see comes out of Facebook research and a lot of collaboration between Google and Facebook. But so we go from standard, it's obvious what we're trying to detect, at least, to it's not so obvious. So how do we solve that? RCNNs, there's a little bag of acronyms coming a few slides later, but so region-based CNN, not at all to be confused with recurrent neural nets. These have nothing to do with RNNs. RCNNs are entirely in the image domain, so it's region-based CNN, and there's a process. I'm not going to spend too much time looking at what some of these other techniques are, but these are all building blocks that reach out to the Retina Net stuff that we'll talk about. So you're going to start with the input image, and look to pretty much find all of the ways that we could slice and dice this image, everything that's a proposed sort of region, and then we'll do some specific techniques for the RCNN to convolve those almost. The backbone of this is really the same CNN that we've been using for 12 years. So we're going to still take the features out of those, and so you run these dense nets and look at the very end for the most part. I'm going to smoothing that over a little bit. But within the final layer of the CNN is where you're trying to take out what's really happening in there. And this is similar to trying to take a CNN with say 50 layers, and then a lot of, a trick is to sort of, or to the way to customize it for yourself is to take a pre-trained network, start there, and train it for your classification at the very end. Similar kind of concept here. You're taking all the optics that are learned in the CNN and hoping that you can find more out of it. But you're classifying the regions, so multiple different ones. However, it's very expensive to do this, so that was proven to work. It was proven to do what was needed, and since then we're sort of trying to make them better. So fast RCNN, it's pretty much the same one person coming up with all these methods. So a year or two later, we've got fast RCNN. So the RCNNs are good, but it's kind of complex. You go from CNNs to SVMs, bounding box regressors, unstable, you'll see. Sometimes it's difficult for these things to converge, or was, and it's expensive mainly. That's a lot of where we're headed here. That's where we're headed if we look ahead to where Retina Net's at. Train is expensive, especially the inference step, so object detection is slow. So what the fast RCNN really does is shares the computation. I won't profess to be an expert at this, but I was surprised to see in the last couple of days when I was looking this up, it actually kind of flips the tables and it runs it backwards. So it's going to do the image classification first, put the region proposal last based on the final CNN features. And really, both methods kind of do that as well, rather than cutting them up. And I guess I say that because we're looking ahead. We do it differently now. So when we look at what Retina Net does and some of these anchors, actually Retina Net doesn't, but faster RCNN, we're going to take a whole bunch of anchors. So different ways to try and speed these things up. Oddly enough, so the faster RCNN is going to add a different step, but it's able to not explore quite so many regions this way. We've got the same convolutional layers, the same backbones, and I'm going to say this a lot, I guess. So something really interesting about all these techniques is that you're going to use your typical CNN as a backbone, which means you're just going to take something off the shelf, use it, and build on top of it, and that hasn't changed. All of these pretty much do that. So we'll take a look at where Retina Net's at with that as well, but you can do the same with the faster RCNNs. Let's take a look at Retina Net. So there is faster RCNN, but it's still, we're looking to go faster. And something that's sort of omitted in this talk, that these are all two-stage methods. Everything I've showed is a two-stage method. The highest accuracy has been two-stage methods until Retina Net came along. So people were looking to try to shortcut this to get speed. There are a bunch of ways to do it in one shot rather than two, rather than looking at the proposals and then actually classifying things, which is slow, which is actually looking at all those features. So with Retina Net, we have a one-stage detector. When we look at the paper does a much better job of describing this than I do, and it's a great paper. I would say very approachable. It's 10 pages and really easy to read, and they do a pretty good job of introducing the state-of-the-art in the front of this. And where Retina Net was at, and what they solved with this paper was to look at when people are trying these single stage, and they're aiming specifically for speed. If you look at where, for example, YOLO, so that's you leave one out, you only look once. The paper is all geared towards the speed of this. The accuracy is not necessarily there. It's gotten better over time, but the speed, and the speeds aren't, it's not like completely game-changing speed, but it is still much faster. So to do this at scale, the speed is definitely interesting to the biggest of the bigs. So Retina Net's really looking at this. Okay, well, we have these one-stage detectors. If you're going to use them, you're going to take an accuracy hit. We know that, but it's still worth it to do that. People are doing this. So we sort of took a hard look at where some of these one-stage detectors were failing and found a way to solve it. And that's really what this paper is about. What Retina Net's about is this focal loss. So the new loss function, focal loss, causes to focus on hard examples. The paper will show very clearly, actually, right up at the top. So there's an architecture here which is proposed in the paper, but if you really think of what the paper is, what Retina Net is an instantiation of this, but the tone of the paper is perhaps other ways would work just as fine. They're actually using off-the-shelf stuff again. They're going to use ResNet as the backbone, a feature pyramid net, an existing way of sort of taking that information and going further with it that Retina Net's able to borrow. But the lot, which had already been done. So the feature pyramids were out there, but to try and hit the speed goal. But what they decided was the loss metric is just all wrong. And so why they're saying that. So what the paper is going to talk about, and let me switch over to it. These are some of your losses here, but I'm going to describe a little bit of what the paper is going to say about the loss function. So in a lot of these detectors, they're out finding thousands of potential boxes. So I've kind of zoomed right on through and provide all the resources, tons of resources for this as I've used to sort of catch up myself. But what was going on there is that there's lots of, their job is not just determining what's in the image. In fact, if I go back, sorry, let's pay attention to this one here. A lot of what we see is pavement and buildings. So a lot of this, there's nothing of interest here. And so foreground, background is a big concept to all of these RCNNs, pretty much all of the object detection. That's one of the main jobs, is determining whether this is interesting and whether they know what it is or not. If it's in the background, it's determined usually not to be interesting. At least that's how these are designed. So it's a big step in trying to figure this out. But what it means is a lot of the information, a lot of the proposed boxes are boxing things that aren't of interest. And so the paper has noticed that it's actually a tricky task because we have lots of easy things to classify. So when we're trying to classify the pavement on the bottom, it winds up very easy to dismiss it. And if you think of cross-entropy loss, a lot of times what it's going to keep doing is keep refining that loss. It's going to go, you're in log space, so it's going to keep pushing from 90 to 99, 99 to 99.9. It's going to keep moving through in some cases, so it's going to keep focusing on these ones that we really don't care that much about, particularly in this background scenario. The same problem could exist in multiple domains, and for me this is kind of interesting because the point of focal loss is really, it's a loss metric. Like, this is machine learning almost 101 of how we do everything, but the idea of focal loss is almost inverted of classic kind of machine learning, where we're going to go from squared loss. A lot of times when we're solving these regression problems, people want robust regression. It moves in a way where we focus, where we stop paying attention to the outliers. What focal loss is almost the opposite. We actually start paying attention to the outliers, but it's in a very different way. And so if you look at this, this is our probability of ground truth class. And so if we think of the right side is the easy detect sort of stuff. If we're, there isn't much value moving, especially in where we have so many different classes possible. If we're at 95% probability, what this does is downweights the interest of that. It's not interesting that, the left side, let me introduce that a little better. So their loss function, what they're going to say in this paper is that it's actually, they're looking at curves that move you from the blue line, which is the most flat, I suppose, if you will, to all of these other curves are just different heuristics as far as how much you want to push the loss down. What the paper says is really, it's just a good idea to use any of these other numbers. The worst thing you can do is use the 0, which is the classic cross entropy. If you start to push your loss curve down towards the green, that's how we can actually start to achieve, we can start to ignore the background quickly and not have these algorithms paying so much attention to these. And so that's a fairly novel concept at the time. Well, it still is actually. This is fairly recent. You can see 2018. So, this is fairly recent. Retina Net's pretty brand new. While we're here, the name in the middle, he's the one doing all the work on the RCNNs anyway. So Ross Gershik out of Facebook Research. Well, as you can see, Facebook AI Research. He's RCNN, faster RCNN, pretty much involved with all those. And this one as well. So focal loss, this is where Retina Net comes from. And so what the paper is going to show that, which is why I think this paper is very approachable. This is not really proposing a specific anything. They go almost above and beyond to say, do whatever you like. Use whichever one of these curves you want to. It's better than anything. At some point, they're going to say there's a couple default values, but they say again, as long as you just don't go with 0, you go with 0.1. Anything will matter. So it's robust. That's really the point they're trying to get through with this for Retina Net, is that this idea is robust. And as it turns out, it is fast, as these single-stage detectors that they were really aiming for, but it's also the most accurate. So when this was published, it was the most accurate on some of the data sets. So I said I'd introduce a whole bunch of acronyms. One of those I haven't yet. But one of the acronyms that's kind of important, the COCO data set is the one that we're sort of all paying attention to for a lot of this. I should have a slide on that, sorry. Here we go, COCO, common objects in context. So a lot of these open data sources, these are fantastic. Coming from a regular machine learning data set, short of these UCI benchmarks that nobody really wants to use because they're all kind of too tiny and don't fit real business scenarios, the image world is actually fantastic as far as continuing to push the bar as far as these open data sets. So we had I'll probably say it wrong, the CFAR 10, the 10 class, the 100 class versions back a while back. Now we've moved on, and this keeps happening. Google's putting out new ones to push the bar of what image detectors can really do, and they're open. The nice thing about COCO is that there's something like 300,000 different images. I might get that number wrong. Let me go to the site real quick to actually point out what we have. So I think this is Microsoft. So what do we have? 330,000 images, 200,000 labeled. And so what's interesting is this becomes sort of a pure research way. People submit the results, and it's a curated method of trying to check that the results are what they are. I see this a lot in a lot of the published articles. There's only so much you can do, and can you trust that somebody didn't tune all their parameters, and then show you what a loop looks like that works pretty well. So here, it's not as hard to cheat as in some of these smaller data sets and the open data sets that 20 years back. In this whole object detection, COCO is one of them. I don't know the new acronyms, but I've seen them. Kaggle has a lot of these out there because Google is very active in trying to create Kaggle competitions that push the bar as far as object detection. So it's pretty exciting. But what Retina Net is measured, and sort of everyone does, the right hand side. So we have here, so inference time, the speed, and then the accuracy is on the left side. And so in the world of object detection, the metrics are a little foreign as well. And so people are measuring themselves on average precision, mean average precision, MAP. But it's sort of challenging on how you do that too, because what we're really doing here is looking at, did we get all those boxes right? And so, is this box right, yes or no? That's not really a classification problem. Kind of is, kind of isn't. So we could circle the whole picture, 50 times and get them all right, but obviously that won't work. And so a couple different of these acronyms in here that are coming out. Down towards the bottom, we've got a couple of them. So IOU, intersection over union. That's an area overlap, so divided by the area of union. So if you think of what the real answer is, so the labels here look different from a typical label. It's a bounding box is the label, and there's going to be multiple per image. So we're going to take the actual label bounding box, compute the area of that, the area of our prediction. We're going to see the union, the whole area of both of them put together, and we're going to divide the overlap by that. And typically, the way that we call a true result is going to be if you can get 50% of it right. So if the IOU is 50 or greater. Now there's a few of them, that might matter to some people and might not matter for the others. But MAP 50 that's usually what they mean. They mean IOU 50, but you see a lot of times in the papers they'll actually go to other lengths as well. 25, but usually it goes higher. 60, 85, I think I've seen. But the metrics are sort of foreign, but that's the way that everyone's starting to measure themselves. And that's what we see here, so they just sort of multiply by 100. So the state-of-the-art COCO AP is sitting right in here, in this sort of 30 to 40 range to make it wide. So here they're showing the two of their classifiers, B, C, D, E, and F. So you can sort of see that they've kind of hidden the chart. But this is the little table of various competing technologies. So you only look once. A single shot detector is SSD, and a few other things in there. But again, state of the art sort of things, and it tends to be Retina Net is better in both dimensions. That said, YOLO v3 has sort of come back, and on some benchmarks, it's actually gotten a little better. Although overall, it seems like Retina Net still has it. But this is where, and so that's part of what attracted us in truth, all these get used in Kaggle competitions, and so Brandon and Shiket had experience using several of these sorts of techniques. There's one, I haven't mentioned it here, which is sort of the one level. If you look at object detection, there's one more level that beyond what Retina Net and everything I've shown does, and that's going to be Nascar Cnn, and that's if you were to take that same image. Sorry for the bouncing back so much. It's a good image though. If we were to actually cut some of these boxes and actually highlight the truck itself and ignore some of the backs. So the box is sort of, you get 2 dimensions, width and height, and you want to include everything typically with these. But the actual pixels themselves are typically, if you're driving a car, that can be pretty important. So Nascar Cnn is another way of taking that one step further, where you actually put a regression layer in there. It's actually, in the output is a mask of a 0 or 1, so it's going to take that same box, but then take it one step further and figure out the actual pixels there. For our task, we've actually used Nascar Cnn a little bit, but only because we happen to have the code laying around. For our task, we don't need these so much. We've paid more attention to Retina Net and the sort of things I've shown on the screen, the classical bounding box sort of detectors. Classic is just a few years old, really. But so I think I've said most of the points of the paper, but again, I would definitely encourage you to, it's 10 pages, you have a couple, of citations, but the way that they go through this paper are great. The resources they cite, the acronyms, I found myself like, what is this acronym, having to read it up? That's where my bag of acronyms came from, because I forgot the SSD and YOLO. But it's the same things that we've been seeing as we've explored these things the last 3 months for our project. It's the same sort of stuff, and they take you straight through into what the actual problems are very quickly. And it says fairly, and here we have the object detectors, the 2-stage detectors, 1-stage detectors. So they're going to do a better job than I can of describing these, and it's very clear. The paper is very approachable, I would say. And the main point, moving from this balance cross entropy away to a focal loss definition. There is, again, an implementation in here. So that's the Retina Net detector that they've actually pushed through. So that's what we have on the slides. All right. So the Retina Net. So we'll take a look at the code a little bit briefly, but we'll take a deeper dive into the code in a little bit. So let me back up a little bit and how we actually get to our instantiation of Retina Net, what we've been using. Is to introduce the business task a little more. So the problem we've been trying to solve for the last 3 months is to take business documents, and namely something, if you think invoices, receipts, things like that. It says there are some bank documents we want, but a lot of report style data. So and we're trying to do entity recognition out of those for sort of the technique there. And so you have a lot of NLP. There's a lot of NLP we will work with, some of which we've scratched the surface of to try to get this to work. But in a lot of these business documents, the NLP is not so clear. I shouldn't say a lot. Actually, NLP does. OCR does a really good job. A modern PDF has embedded a lot of the text. The structure is there. There's a lot of good stuff you can do with NLP. But the last mile, there are things that will be difficult for us if we can't get that last mile done. And so we have started to approach the deep learning in 2 ways. To use it as an ensembling technique. So, even if we have NLP methods going to try and extract some of these entities out, jumping a little ahead, we want to use it as a companion technique. But there are some things we don't believe that the NLP methods will even have the data in front of them. We don't believe we'll be able to capture all of the text behind and all the meaning behind some of these documents. And so we want to explore these deep learning techniques to be there when we get there. It's a little bit almost overkill at the moment where we're at, but we're going with sort of baseline text methods. But we are definitely exploring. We've explored quite heavily these deep learning approaches, the image recognition approaches for this. But what we're doing, you can see sort of an invoice on the side. And so what we want out of it, namely, in this document, there's different targets for different documents for us, but we're pulling out the date of the invoice, which is interesting because there's judgment. There's a lot of dates on these documents. We have a specific date that we're interested in for our purposes. And so that becomes, trying to find it isn't so much as just a date parser. We don't need to find all the dates on the invoice. We need to find the one that matters to us. And so training is crucial for that task. it's treated like a classification task rather than just a basic retrieval. And most people ask a lot why we don't just use OCR to do this. But if I have 7 different dates, particularly if they all match, I need the correct one, and I need to show people where we got the correct one from. Invoice number, we have a table here, and so what we really want are the little pieces of the table out of this. So you can see one looks like there's about 3 items in here. We want the information as you would read it, as you put into an accounting system, namely, as you would, the quantity, the price, what that totals into, maybe tax, things like that. But what we've run into, move ahead a little bit, is that it's difficult if we go straight for all those things. If we start to look at maybe 4 or 5 columns in that table, 3 rows, all of that, so far, to be honest, we haven't had good luck trying to get after that with a one-shot sort of technique to go after it. And so, but what we have had a little better luck is in identifying the table structure here. And if we can do that, perhaps throwing that into an NLP algorithm or focusing our deep learning approaches so that they don't have to worry about all the header sort of stuff. But it's interesting that there's a couple different ways to slice this problem. So we're in the applied domain. We're taking this task of trying to figure these out and using whatever techniques, anything under the sun, but it's led us to Retina Net so that we can start to do this sort of task. So we can use deep learning to start to teach it what the table looks like, what the tables of interest to us look like, where they are on the page, what that looks like. And I'm speaking of giving kind of personification. That's what we hope they're doing. In truth, it's hard to tell what they're really doing and why they fail, and that's been some of our tasks. So again, is this a problem? OCR, not entirely, and there's some critical mistakes that OCR makes when we're trying to get all the text out of there. If we could get perfect text every time, we might not need deep learning. We'd still need some judgment tasks, but we could probably get away with it in a lot of NLP. But there's a couple interesting things. Watermarks are something interesting for a lot of these documents. The best way for us to go after the information is not any text that exists. It's actually who issued the document, and they tend to announce themselves by having a watermark up at the top of the screen. And so that's something that's really interesting for deep learning. NLP techniques are really bad at that. With OCR, the best you're really going to do is get the BDO out of this document. That it's a watermark, that it's huge compared to the rest, are not typically coming out of OCR engines. And by that, we're using Tesseract, which is fairly modern OCR. It's using deep learning itself in 2 different ways. You're using image recognition to do the text recognition. The modern ones are doing the LSTMs to do the NLP side of things. It's really good stuff. But we don't think it'll take us everywhere we want to go. And that's what sort of makes the use case for us to explore what we have. So I'm going to kind of blow through this one because we sort of talked about it. But we envision NLP techniques of various types, image recognition techniques, all kind of being ensemble together. So we want that other opinion. But we also want to use it in some cases where we think we probably will have no other option, or in this case, maybe, again, like the watermarks. Not that we have no other option. A lot of times it's there somewhere, but the tell feature, the giveaway feature is really that watermark. It's one of the things that are important to us. So where are we at? So our results, Faster RCNN has done pretty well. That's sort of the last stage of where we it's one stage before Nascar Cnn. We tried Nascar Cnn, it actually does okay as well, although we just don't need the math very much. And we don't have good labeling for the math, in fact. Interestingly, YOLO v3 is definitely done, that's 2018 kind of thing. That's really up there with Retina Net, neck and neck. We tried it first, and we've seen some other people trying to solve this same task, particularly the one with the table and the header. With YOLO v3, because it's sort of an off-the-shelf kind of thing. It's really almost near appliance level when you're doing some of that kind of stuff. Interestingly, we haven't had good results at all with YOLO v3, but Retina Net is really where we had the best results so far with Retina Net, and it's intriguing because of what we see on the next slide, because of the backbones to me. And so technically, as I said, as I've learned with this talk, this is sort of Brandon showing us the backbones of what he tried, because it's so easy to loop through this implementation. That's really where our code is to loop through backbones and see what happens. If you read the literature, ResNet seems to be the only place to go. Interestingly, if you look for this table, for our task, and our combination of whatever it is about our use case, Retina Net is by far in last place. Perhaps that's why YOLO is also not great, not sure. So again, in truth, we could have run other backbones through some of the other techniques, but it makes it very easy to do with Retina Net, and that's sort of where we've been at. So we've been chewing up our GPU server by just looping through these backbones and sort of measuring what it is. So it's applied. That's really what we're doing, trying to figure out how to use the techniques, how to push them in, and see what happens. But to me, that chart on there has been one of the more interesting things because those are worlds apart. If we look at the DenseNet for us is doing the best, you have these 0.391s that's similar to 39 in their space. That's not to say that's not the same. Our task, I think, is in many cases a lot easier on some of the classes that we're going after. In fact, you can see this on kind of the right side. If we look at the right side, the average precision of two of the things we're going after for this particular document are extremely high, 93 and 88. It's doing a very good job at figuring those out. However, most of the other classes are really bad or maybe okay. The stock code 29. Not so important what we're going after here. That's our task. But something you don't see too much is people trying to break apart the classes. Are there difficult ones? Are there easy ones? And perhaps in the generic COCO data set, maybe it's sort of balanced a little more. To be honest, I don't know. But in our case, it definitely isn't. And so, from a practitioner point of view, these are kind of the ways that are interesting. Can we, and therefore, in the ensembling domain, in using all the tools under the sun to try and get your task accomplished, I'm actually fairly happy with these results to some extent, because the invoice date and the invoice number are some of the things that our NLP tasks actually are the worst at. The NLP task, if they can get a hold of a table, they actually can slice and dice through that table really well. You can actually use a lot of different techniques to sort of figure out the table structure, and we're doing very well with some very baseline models. So we have a real opportunity here to start to use some of our deep learning techniques to help us perform that judgment step where some of our more basic and NLP techniques may be failing us or have a more difficult time. So using two things in concert is sort of interesting out of here. It's very likely also that we don't have enough data. I would say that's one of the things we're going to go after. And so, but a little bit, we'll look at what we've modified with Retina Net, I think, first before we sort of talk about our lessons learned. But question? Oh, sorry. Yes and no. We're starting to do that. So we need custom labels for us though. So in some cases, some of these the actual date something was recorded from an accounting point of view, and some of the other things that we're going after are definitely custom to our problem. Now, is the source data readily available? We're starting to get there. I mean, again, we're 3 months in, but yes, we're tracking these down on the internet, I suppose, at the moment, but skeptical, yeah.
No, I'm not skeptical. It's like it's focused on one type of documents.
There's about 6 of focus right now, and actually the other ones are much harder. But we would settle for good if we could get our improvement up on the invoices as they are to get them labeled. But yes, I mean the natural progression here is an Amazon Turk sort of style.
You say invoice.
I'm saying invoice because that's the one we can talk about.
Okay. We can talk offline later. I can show you some arguments.
Sure. And so here is sort of an example of an invoice. And so we're getting some of the things right, we're getting some of the things missed. And I don't want to lose track of time because it feels like I'm going, 41 minutes in. So what we'll look at is our applied version of this, and for the most part, we'll point you to the right resources. It's a very high level of what we're doing, so it wasn't going to be quite a deep dive into TensorFlow of how they implement this, although we'd say it's very easy to use. Probably discounting Brandon a little bit there of what he's done here, but taking this for our problem has been pretty easy to modify. And this is our backbone sort of script, and so we've modified the Retina Net so that we're just really going to bash script. That's where it starts. And we're just going to implement train pi. Just run one sort of thing, loop through this list of backbones. This is the sort of thing that produces the table you saw earlier. So our techniques, we're running early stopping in some of these. These take a while. It's not surprising, doing a lot of these. We are running this on just one Titan X, if I'm correct on this. We do have a DGX1 exposed, but there are various logistical reasons why we can't use it at the moment, but we're getting our data to get shipped over there so we can speed some of this up a little bit, and getting a second GPU out of that system, and we have various GPUs laying around for all these that we're running. Something about our problem that actually I think is sort of the next one. So this is very basic kind of stuff. So the IOU threshold is much lower than I said. I said 0.5 was the IOU threshold we're looking at. For the way we have framed this problem, we'll settle for much less, and that's something to do with some of the lessons learned. I think we need to increase the IOU threshold more to 0.5. But it's sort of the way we've labeled the data, and we've been a bit too cookie cutter, and we're sort of shooting ourselves in the foot a little bit. So we have a fairly low IOU threshold for what we're using, and perhaps updating that, keeping that more in with the literature with 0.5 would help us out a little bit. One of the things I sort of wanted to call out here that we're sort of doing for our implementation, we've turned off a lot of the randomization as well, and we've actually kept some of our translations. So the augmentation step is very minor in what we're doing. In fact, with our problem, we can get thousands of different versions that look very similar to the same basis. And so the augmentation step is actually not really much of a problem with us. It's still useful to use a little bit of the augmentation we have here in TensorFlow, but we have that in spades. We have tons of data as far as that. What we need is a lot more randomization. So the things tend to overfit, and I think that's really what's we're seeing with some of these backbones being inverted from what we'd expect, and perhaps the same with the YOLO inaccuracy. I think we definitely need more variance in some of our data sets, and so that's part of what we're doing in here. So I have some of these lines called out, but again, I know I'm going long as far as time. It tends to be, in my experience with running some of the TensorFlow stuff, you're usually looking at a fairly compact number, of lines of code where you're usually touching a couple things. I would say that this one's spread out a little more. So we have, if we're looking, that's our bash script, but these are actually fairly sizable, but fairly easy to read. So if we're going to go through this line by line, we probably don't have time, but it's pretty stock stuff. If you're used to the TensorFlow models, most of these, you're adding focal loss, but focal loss is just coming out of coming out of Keras rather. Sorry, coming out of Keras now. And so I meant when I said TensorFlow before. So Keras scripts tend to be compact, even though being in Keras here, fairly lengthy, but a lot of it is fairly stock stuff. So we haven't had to customize this too much for what we're doing. So we're taking some of the augmentation steps, customizing that, some of the thresholds, and the data generators, and that's really about it. Otherwise, we're using a pretty stock implementation of the Retina Net that actually comes from the original source. It's been moved over. It's now on Facebook AI, has a detectron, which is really cool. And that's sort of the idea, again, of applied, of rolling through all these sorts of things. It's sort of meant for the sort of thing we're doing, where we're agnostic. In fact, the training time, the inference time is not a big deal. We'll take the accuracy at sort of any cost at the moment. And Detectron out of Facebook makes it easy to roll through a lot of these techniques and see what works for you. So. Lesson learned is sort of where we sort of got into, and so I think what we've been struggling at is coming up with templatized way of making good use, but going from nothing to something. So with a basis number of invoices, can we essentially augment in our own way? Can we move these invoices around where they're sane? We want it to learn the structure of what a human invoice looks like, and file their documents perhaps, and more down the line. But the structure of these, humans have laid this out in a very specific purpose. And so we can't just randomize everything on here. We can't move fields apart from where they need to be. So we need to be careful about how we apply randomization. We need to move groups of things around and have it look sort of sane. But at the same part, we want it to find these groups of information. So it's finding these tactics. And so we started by creating some of these templates and getting a ton of data that we can feed through these in template style, just feeding different kind of algorithms. In the NLP world, that you can get by a little more with that, as long as you're changing the way things look, changing the terms that it uses to call all of these terms we're looking for. We're looking for invoice date, that's going to appear 50 different ways with different acronyms and all that kind of stuff. You also have to eventually do that in a different language, which makes this fun. But a lot of these we'll have to face a lot of hurdles from where we're at today. But we have struggled to give it enough variance with this sort of templated kind of approach. We continue to work towards that, of randomizing more of these while still maintaining a human, sane-looking invoice. We've gone with a couple different labeling styles, and so what I mentioned first is that, in fact, the one you had in front of you, the struggle with trying to label, with labeling these is, you're doing it the way you've seen it, annotating whatever kind of word you want to use for it. So there's lots of services that exist out there. We're using a simple one, having a go at it with our own crew to try to get our way of doing it correct, and then crowdsourcing it. If we could find, having thousands of documents, letting the crowd label these things, the trouble is we can't settle on exactly what we want either. So as we've moved from a world where we're trying to identify, if you look here, quantity, stock code, description, every one of these table columns here, it really just hasn't worked so far. So, however, again, like I say, in the NLP domain, that actually is the easiest part of this whole exercise. So seeing where we are, moving, experimenting, failing fast, and moving forward has at least saved us from trying to, send these labels, relabel these about 50 times over. But that's the process we're at, is that we're back to simple. So here we have a table identifier of 2 different tables, and we're trying to push those through. So sourcing these documents is really where our struggle is repeatedly, interestingly enough, but we'll have to finding better ways of doing that, and then using the cloud, using the crowd, honestly, to start to label these is one we're doing it. And we're always working with the customer who's working with this, who's located a lot of these, but then we have different kind of concerns. So lesson learned here, so far, the thing that's been hurting us is trying to synthetically generate data. It just hasn't worked. The deep learning has outsmarted us in all these cases. We're looking at things that out of fold look really good, and then all of a sudden we do it the right way, and we realize, no, it was able to cheat because we weren't smart enough about moving things around the page quite enough, and it actually was too similar to the other stuff. So sorry to speed through and the code demo there, but if you want to go ahead and go around for questions, and I'll be across for drinks so we can answer any more of these, and we'll put a lot of tons of links I can provide, definitely a lot of cool repos. For me, I guess the biggest takeaway, as you hear me say many times, the paper, very approachable, the implementation, fairly easy to use, especially with a few, you're just getting pretty quickly up to speed on the sort of concepts of where you might actually change and customize for your own problem. So the data generator is very similar to, if you've worked in Keras, this one is somewhat easy. So, yeah. No, definitely not. Yeah, so our invoice is going to have a custom model for that.
Can you repeat the question?
Oh, yeah, sure. So the question was, are we using a single model to handle all types of documents? We may find use of, for this header style one, a table is a table is a table. We might be able to get away with that. So we're trying that. So far it hasn't, but no, it's certainly at the end of the road when we have some of these things like invoice date and things like that. It's going to be custom for its particular type of document. Oh yeah, in fact that's what we really need. So we need yeah. In fact, if you look at people trying to do this, a lot of the ways they do it is teach you how to learn, almost memorize an Amazon.com invoice, and then you're good to go. And for a lot of clients, there you go. That's 10%, 20% of their business. Find your most common clients and memorize those. There's a lot of cookie cutter algorithms out there. That exactly, yeah, that won't fly for us. Yep.
The Retina Net you're using is actually one that's being trained on
Yeah.
no.
Oh, good point. So no, actually, we're training it ourselves on these documents. Yeah, so off the shelf, we have customized it for our own purpose. In fact, we're starting all the way from scratch to the point. One of those comments we didn't get to in the code is we're just starting out from straight old ImageNet all the way from the back. That's where it starts, and training it for our purposes. We have experimented. We've pre-trained models in the past, but no, it's an architecture off the shelf. So sorry if I'm using the wrong lingo here, but. An architecture off the shelf combined with other architectures off the shelf to make this thing happen. It is, yep. Okay. Sure, absolutely. Yeah. What kind of throughput? Yeah, in the wild. So we would expect there's a couple, if you think of an INJ loop, so the actual, our clients' would do this for a fairly small amount of documents at one time, but we may have that our clients maybe go through many of their clients at the same time. But we do, that's where I say the speed, at the moment, we, say this today, in 2 years when you actually get productionization, you always want more speed. But so far, we'd be doing this on order of hundreds of documents for the client's client, and then again, they may multiply those all the way up to something hundreds of those at the same time. But we're not doing it Facebook, Google kind of scale where the cloud could be providing a document every thousands per second. Does that get to your question? Yeah. Yes. Yeah, for this task, it's just the rasterized one. So definitely the idea of using meta-channel information and trying to get some of the stuff out of the NLPs, lots of things that we may need to understand. Yes, that's definitely, it's on the radar, but so far it's just been turning it into a PNG and dumping that in the same kind of typical preparation for the images. So, if I didn't repeat the question, that was, how are we using the rasterized image or the PDF itself? And so when I say the actual PDFs are going to come with typically embedded text, which could certainly be useful. We have not explored how to use that so far. And in fact, so far, our experience in the past has been difficult. So if anybody has good results of using different kind of misaligned channels almost, I would definitely use the wrong terms here, but meta-channel is kind of the way Shaket's always talked about this when we've explored there, but something where we don't, your RBG channels are all going to be fairly well aligned. Brandon and Shaket have had difficulty trying to augment that with other things that don't look the same shape, but it's not to say that would be a good path, certainly, and taking any other features we could use, to see this really be kind of a loop together, a system working well together. Other questions? Yeah. Yeah, okay, so the question was, has anybody looked at focal loss as far as boosting? Well, I guess, so, as I showed, most of my Kaggle competitions are on the transactional side, and in fact, I met John doing GBM talks, so, and was my role at H2O first, so, yeah, using, the GBM algorithm itself, it's that version of boosting. There's different types of boosting, but the idea of boosting is that you have an arbitrary loss function. So to be honest, you could actually apply, if you wanted to, and they've certainly got the derivatives worked out for this thing, that's the whole point of getting this to work. And in fact, in the paper, they're going to show there's a slight modification they make to take the simplified version of this function to make the derivative a little cleaner. They've got one sort of addition to this. It introduces a term, but that's the term that they say is that really that you don't have to tune it very much. It's almost any number will do. So for boosting, could you use it? And that's where different loss functions are there. I would say, in experience, the loss function hasn't mattered as much as I have seen, and I've not seen anybody trying to boost deep learning, I suppose. So boosting, for those who don't know, would be, it doesn't have to be applied to decision trees, it just commonly is. Linear learners occasionally will do okay, but it's taking a weak learner, decision tree, linear model, not all that great, but solving the problem, taking a weak one, and then solving for the residuals effectively, and so it looks very much, taking the same sort of derivatives you have to acquire for deep learning is what it takes to do a boosting round. I think you could try anything, but I'm trying to look at the robust version of that, where you look at Laplace loss, Huber loss, that kind of stuff. If your domain calls for that, I think so a key element of why they find this to work is the enormous amount of disparity between the class imbalance. So by the time you run all of the, I hope I'm using this term right, thousands, it's that or more. So the numbers in one of these when they compute how many different the proposal step and the anchors, whichever way you're kind of doing it, is sending back potentially thousands of different candidate images. And so what they're having to deal with is most of those are easy to just turn down. And so that's the reason they're using this focal loss, And I think in classical machine learning, or I guess the places I've seen boosting used, you usually don't have that circumstance up front, but it's definitely been discussed at H2O. Can you flip this? Like maybe rather than go with the else.
That's kind of like conceptually, so go back from
Focus on the hard ones. You're right. Yeah.
They kind of zero in, if that kind of tried over to say zero in on the
Especially the original boosting, the 99 paper. I'm forgetting all my authors and terms, but it's true. Yeah, it was purely upweighting the ones that are hard, which made that difficult. It made it go after the noisy examples and in fact the incorrect ones. And I do believe that part of this paper they do mention that anecdotally it's important to make sure your labels are correct. In our case, the labels are not great, but for a different reason. But the labels are generally fairly accurate to what they're supposed to be. But that might be a gotcha of using one of these things. I don't know. But if you somehow your application has a high level of noise, yes, this might actually fall down the same trap of boosting. But you're right. That's exactly why boosting in the 90s was tough until the GBM part of it came in, and we took different loss functions and were more robust at that point. Yes.
Mark, thank you so much. That was a fantastic talk. Just a reminder, CU29, right across the street. Probably we'll leave here in about 5 minutes, so talk amongst yourselves, and we'll head over there. Look forward to talking to you. Thanks for coming out.